Okay, welcome back. So we are going to look at how we can calculate the moment of inertia of a rod by integration. Okay, so here we assume we have a rod that has a uniform mass distribution, say lambda, we call it lambda. Okay, then we are going to first calculate the moment of inertia of such a rod about an axis that's perpendicular to the axis of the rod and that passes through its center. And then we are going to also calculate the moment of inertia of this rod about an axis that passes through the end, and that's parallel to the first axis, okay, the axis that passed through the center. That would just be an application of the parallel axis theorem, which we saw in the first, the introduction to this series of videos. So if you haven't watched the introduction, I will put the link somewhere here or here. So make sure you go and watch the introduction first. It's useful before coming to this one. Okay, so the idea here is to first choose a small element of mass of this rod. So we are going to define a tiny element. Let me maybe use another color. So let's say we choose this element, an infinitely small piece of that rod. Let's say it has a distance of x from the axis that passes through the center. If you want, we can call that axis delta. Okay. And then it has a mass of dm. So it's a very tiny mass. Lambda is the mass distribution, which means since the mass is uniformly distributed all along the length of the rod, lambda is just going to be the mass of the rod, in this case capital M, okay, all over its length, capital L, because the rod has a mass of M and a length of L. This then also has to be equal to the elementary mass, which is dm, okay, divided by the elementary length, which is d, we can call it dx, okay. So just suppose that this mass dm also has an elementary length or thickness dx, okay. Then the moment of inertia of this rod about the center, let's say I center, okay, is going to be the integral of the moment of inertia of this elementary mass dm. And what's the moment of inertia of this elementary mass dm? It's the mass itself, so dm, times the distance from the axis of rotation, which is x, and then we square it. Okay, so we integrate over all the mass m. But then we can replace the expression of dm from here. So I center, I'll just call it C, okay, it's going to be the integral of x squared times dm. We can isolate dm here. That's going to be m over L dx. So we replace that here, we are going to have m on L dx. And then we do that for values of x ranging from negative L over 2 to L over 2 in order to generate the whole length of the rod. So L goes from negative L over 2 to L over 2. So doing that, we are going to have, we integrate x cubed because this is a constant. So that's going to be m over L times x cubed over 3. And then we apply the boundaries of integration like that. So that's just going to be 2 times m over L times L over 2 cube, okay, divided by 3. And if we simplify that, we are going to get IC as 2 m on L times L cube on 3 times 8. So that's going to be 4 times 3. So that's going to be 1 over 12 ml squared. Okay, so we obtain IC as 1 over 12 ml squared. Okay, so this is the moment of inertia of a rod about an axis that passes through the center of mass of the rod. Then we can use this result to calculate the moment of inertia now about an axis that passes through one end of the rod. So this is just an application of the parallel axis theorem. So let's say you have I end, okay, it's going to be equal to I center plus the mass of the rod times the distance between the two axes squared. So that's L over 2 squared. So this is going to give us, let's say, IE. That's just going to be 112, then ml squared plus m times L squared over 4. So if we simplify this, that's times 3 here. So that's 4 on 12. So that's going to be 4 on 12 ml squared. And simplifying this further, we get 1 over 3 ml squared. Okay? And this is the moment of inertia of a rod about an axis that passes through the end of the rod. So it's really straightforward. So far, it's just an application of the theorem, the parallel axis theorem, to deduce this. Really easy. So the difficulty, usually, when calculating the moment of inertia of a composite of a mass distribution, is to be able to choose the right elementary mass and then perform the integration correctly to get the result. Okay?